of needles. The package then goes into a special rolling mill. It spins in this machine for 2 days. Inside, the needles agitate with the polishing ingredients, and they emerge looking much smoother. Then it's into a washing machine for a scrub with soap and water. This removes the polishing residue to prepare them for electroplating. Electroplating gives the needles an outer skin of corrosion-resistant nickel. The needles now move forward into a sorting system that ensures the needles are pointing in one direction. An inspector examines the needles for flaws and sorts out the defective ones. They dip the eyes of some needles in a gold bath and apply an electrical charge so the gold gravitates to the nickel and adheres. A little gold around the eyes makes them stand out, so these needles should be easier to thread. Meanwhile, the production of pins is well underway. Gas jets melt glass into tiny dollops, which stick onto the tops of the pins as they roll by. The glass hardens in seconds, going from transparent to opaque. These glass-headed pins are now ready for hemming and other sewing jobs. The pins fall between 2 revolving cylinders. The space between the cylinders gradually narrows. This sorts the pins by size as they drop into various bins below. Now all that's left is the packaging. The packaging line is entirely automated. Robots drop sewing needles into grooves in plastic packages, and the packages move forward. The timing is flawless. Finally, a transparent cover showcases this product's many selling points. Exterior moldings can transform an ordinary structure into something grand. The ancient Greeks were the first to demonstrate this with elaborate carved moldings on temples. Today there's no need to spend long hours carving moldings. Fabricated synthetic versions are now available to give a structure instant curb appeal. Architectural foam moldings trick the eye. They look like stone or wood, and it's all a carefully crafted illusion to impress the neighbors or passers-by. They start with a big block of foam. It's expanded polystyrene, or EPS. They activate a hot wire foam cutter. Controlled by computer software, it melts its way through the thick foam block to make very precise and intricate cuts. This computerized hot wire is cutting out pieces of architectural trim for windows or doors. It carves in an economical way to minimize waste. Its work done, the hot wire rises, leaving a trail of smoke from the burning process. A worker then pushes out the moldings. Each piece of architectural trim is 2.5 meters in length. The hot wire now carves an elaborate fluted column, 1/2 at a time. This is a Roman-style column. Once carved in stone, it's now being replicated in foam. And this old-world look can now be achieved with minimal physical effort. To make an arch, they use a hot wire shape instead of a computerized straight wire. They position it in front of a curved piece of foam. Rubber drive wheels push the foam through the hot wire. These wheels have been preset to accurately steer the cut. The result is an arch that will be a perfect match for the linear trim produced earlier, so they'll fit together seamlessly. They use a carved foam wedge to emulate the keystone, a piece used in stone arches to lock parts together at midpoint. A worker now wraps the cut foam moldings in fiberglass mesh. Pre-infused with glue, the mesh instantly adheres to the foam. This mesh adds strength to the molding, and it also makes it crack-resistant. Next, cement flows into a hopper and onto the moldings below. The moldings are driven through a template with the same contours to apply the cement evenly on the surface and the sides. This is no ordinary cement. It's a pre-engineered mix fortified with a special resin to create a durable coating for the mesh-covered moldings. A worker then transfers the moldings to a rack to cure for a minimum of 24 hours, before getting another coating of cement, this one with a much finer texture. It's much trickier to apply cement to an arch-shaped piece of molding, so they take a more hands-on approach. The employee scoops the cement onto the meshed foam semicircle. He then moves the custom-made template over the molding, instead of pushing the molding through it. It's a better way to evenly distribute the cement on a curved surface. After carving, meshing, and 2 layers of cement, this arch is now ready. For smaller orders, they also apply the cement manually. There's no need for a machine setup when there are only 1 or 2 columns to be coated. Guided by a track on the side of the table, the worker slowly draws the template down the Roman-style column to apply the cement to the foam and make it look like stone. The second layer gets extra attention. He rubs the cement into the grooves for complete coverage, and then pulls the template across once again, this time lightly skimming the surface to produce a finer texture. And now, these moldings are ready to add detail and definition to a structure. A locomotive is the powerful vehicle at the front of a train which pulls the cars along the track. Sometimes there's a second one pushing from behind as well. Passenger train locomotives are smaller and designed primarily for speed. Freight locomotives pulling rail cars are significantly larger and stronger. Heavy hauls are mammoth freight locomotives designed for North America, where tracks are wider and stronger than in most other parts of the world. Those smaller yellow locomotives are for the European market. The larger gray ones, to the right, are heavy hauls. Workers weld together massive pieces of steel to construct the locomotive's structural underframe. At each end, they insert a giant steel pin through a hole in the underframe's floor. For now, they weld the pins partially to tack them in position. Lifting and maneuvering it with giant trunnions, they flip the underframe so that the protruding side of the pins is facing upward. A crane system transfers the underframe to another area to complete the welding. The pins require exceptional bonding because they connect the underframe to the wheel frames. An automated welder circles each pin repeatedly, progressively building up a 2.5 centimeter thick weld. They make the same size weld on the other side of the pin. All the welded steel parts are exceptionally thick, rendering the underframe strong enough to pull 454 metric tons. Next, they install the air reservoir and pipes for the pneumatic brake system, and a 20,000-liter fuel tank. Then they assemble the locomotive's 6 traction motors. Each one generates 750 horsepower, 3 times more than a typical car, giving the locomotive 4,500 horsepower strength. To build each traction motor, they bolt coils of wound copper into a cylinder called a stator. Then they lower another cylinder, called an armature, into the stator. Powered by an alternator, the coils produce an electric field that rotates the armature, turning components which propel the locomotive. Workers lubricate the wheels. Then, using a strong press, fit 2 on each of the vehicle's 6 axles. Each wheel is a meter in diameter and weighs about half a ton. The axle has a large gear that turns both wheels. This finished unit is called a wheel axle gear assembly, WAG for short. Workers install a WAG onto each of the 6 traction motors. The WAG's gear engages with the traction motor's gear, so when the motor runs, that gear turns, which then rotates the WAG gear, which turns the wheels. So now there are 6 WAG and traction motor combinations. Workers divide them into 2 groups of 3, then bolt each trio into a frame called a bogie. So now the locomotive has 2 bogies, each with an air-driven brake system built into it. Until this point, the bogies have been upside down. Now a crane flips them right side up to prepare for the final assembly of the locomotive. They position the 2 bogies next to the underframe at opposite ends. Cranes then lift the underframe and slowly lower it onto the bogies. The pivot pins protruding from beneath the underframe drop into receiving holes in the bogies. Next, they lower a giant alternator onto the deck of the underframe. It powers the traction motors as well as the control systems and other auxiliary equipment. This 16-cylinder, 4,500 horsepower engine drives the alternator. Next, the operator's cab. It's insulated for sound and sits on a shock absorber system. Then, the various electrical hookups, including these thick cables. Each one contains more than 1,000 wires, carrying nearly 10,000 amps. Now a hood goes over the engine and alternator to protect them from the elements. From here, the locomotive goes to another department for paint and decals. The finished locomotive is almost 23 meters long. Fueled up, it weighs 204 metric tons and, depending on the terrain, can haul a train up to a kilometer long. The first clothespin was invented in the early 1800s by the Shakers. It was a cylindrical piece of wood with a vertical notch cut into the bottom. In 1853, an American inventor patented a spring-loaded two-piece lever clothespin. That's the type still produced today in both plastic and wood. This Czech company makes clothespins out of beechwood. Beech is ideal because it's hard and durable. When the logs arrive at the factory, an automated bandsaw slices each one laterally into 7-centimeter thick planks. Wood is naturally damp, so it's critical to dry the planks. Otherwise, clothespins made from them would repeatedly expand and contract with temperature changes and eventually crack. First, the planks air dry outdoors for about 7 months, until their moisture level drops to 20%. Then the planks go into a kiln for 3 or 4 weeks, to bring the moisture level down to between 8 and 10%. The wood now stable, workers cut the planks into shorter, more manageable lengths. Then into 7 by 7 centimeter blocks. Next, they feed the blocks into a cutting machine. Its 4 circular blades simultaneously saw through each block, cutting it into 5 pieces. Each piece is 9/10 of